Every day, thousands of airplanes cross the sky. But when a machine weighing hundreds of tons transitions from the stratosphere to the ground, it enters a hidden, hyper-coordinated ecosystem with a near-zero margin for error. Within this environment, a single misunderstood radio call or a misaligned radar signal can instantly paralyze the facility, bringing the high-speed flow of thousands of people to a complete standstill. For most travelers, the airport is simply a place to wait. They wander through brightly lit duty-free shops and buy overpriced coffee. But the areas accessible to the public represent about 5% of the actual airport. The other 95% is a sprawling metropolis hidden out of sight. The terminal building acts as the sleek, friendly interface for a massive industrial machine. It is an infrastructure designed to solve one of the greatest challenges of the modern era: mass transportation across the globe at the speed of sound. To understand why this environment is so complex, we have to look at early commercial airfields from the 1920s. Places like Croydon in London were social venues first and transportation hubs second, built on little more than wide-open grassy fields. Aircraft of that era were relatively light. A simple unpaved grass or dirt strip was sufficient to absorb the impact of a landing biplane. By the late 1930s, the physics of aviation shifted with the introduction of heavy, all-metal monoplanes like the Douglas DC-3. These aircraft carried heavy payloads and thousands of gallons of volatile fuel. Under the weight of these machines, a grass field would instantly turn into a muddy swamp. Managing the volume of heavy commercial traffic required a transition to massive, reinforced concrete infrastructure. Terminal buildings designed like 19th century railway stations could no longer handle the volume of cargo and passengers. The modern airport had to be invented from scratch to manage heavy assets moving at high velocity. The operation of an airport begins long before the runway is visible. When an aircraft descends through thick clouds or heavy rain, the pilots rely on a delicate interplay of radio waves to find the ground. The instrument landing system projects an invisible radio funnel into the sky. It uses a localizer antenna array that mixes two modulating signals, one at 90 Hz and another at 150 Hz. These signals destructively interfere perfectly down the center of the runway, creating a net voltage of 0 that tells the pilot they are locked on to the center line. A separate antenna mast creates the glide slope using the same signal modulation, but arranged vertically. The intersection of these frequencies creates a straight line angled at precisely 3 degrees, allowing an airliner to guide itself to a touchdown in 0 visibility. Beyond the precision of radio beams, pilots must also contend with the physical byproduct of flight: wake turbulence. High-pressure air beneath the wings constantly escapes to the low-pressure area above, creating violent, rotating tornadoes trailing behind the aircraft. These vortices sink toward the ground at up to 500 feet per minute. If a smaller plane flies into the wake of a wide-body jet, the spinning air can forcefully roll the aircraft, exceeding its mechanical control and causing it to flip instantly. This necessitates strict separation rules based on aircraft weight. Because of these invisible tornadoes, an airport cannot land planes bumper to bumper. Capacity is limited by the mandatory waiting periods required for these vortices to dissipate or drift away in the wind. When hundreds of thousands of pounds of aircraft hit the earth at 150 miles per hour, the ground wants to give way. Distributing this concentrated wheel load requires rigid Portland cement concrete to keep the pressure on the underlying soil incredibly low. Without proper preparation, airports suffer from pumping. As heavy aircraft roll over concrete joints, the immense repeating pressure forces water and soil to shoot out from underneath the slab edges. Over time, this washes away the foundation and leads to catastrophic cracking. To increase capacity, engineers design rapid exit taxiways. By angling these off-ramps at precisely 30 degrees, landing aircraft can turn off the runway at high speeds without needing to brake to a complete stop, drastically reducing the time the runway is occupied. Navigating these taxiways in heavy rain or fog is a challenge for pilots. Older surface movement radars operated in the K-band, where the wavelength interpreted heavy raindrops as solid objects. During a downpour, controllers would see a screen full of ghost targets. Modern airports use SystemX, which utilizes X-band radar and multilateration to cut through the weather.
By comparing the nanosecond differences in when a transponder signal reaches multiple antennas, the system triangulates a vehicle's position with pinpoint accuracy. If a collision is detected, the software can automatically illuminate red stoplights embedded in the taxiway. This high-tech surveillance is what keeps the massive complex from collapsing into a bottleneck of ground incursions. Once parked, a standard narrow-body jet has roughly 40 minutes to deboard passengers, pump jet fuel, and load cargo. At a busy gate, driving hundreds of explosive fuel tanker trucks around the aircraft is a logistical and safety risk. To solve this, airports use a subterranean fuel hydrant system. A network of pressurized pipelines connects bulk storage tanks directly to pavement vaults beneath the aircraft's wings. Ground crews simply attach high-pressure hoses from the underground pipe to the plane's receptacles. To prevent these explosive pipelines from rusting in the damp earth, airports utilize cathodic protection. By running electrical currents into buried anodes, engineers manipulate the chemistry of the metal so it cannot corrode. Beneath the terminal floors, luggage moves through another hidden network. Historically, moving bags was an ergonomic challenge that resulted in significant physical strain and spinal compression for workers lifting heavy suitcases in manual bag rooms. Modern hubs use the independent carrier system, moving one bag per tote. Each tray is embedded with an RFID tag that links the bag to the passenger's destination data. These totes travel through miles of tunnels on closed-loop tracks, passing directly through explosive detection scanners without ever needing to be touched by human hands. The 40-minute turnaround at the gate is made possible by this automated cardiovascular system, pumping fluids and data beneath the concrete. To see how these systems perform under extreme pressure, we look at Mumbai's Chhatrapati Shivaji Maharaj International Airport. It occupies a landlocked 1,900-acre footprint, completely surrounded by dense urban sprawl. Mumbai possesses 2 runways, but they intersect to form a giant X. Because the runways cross, they cannot be used simultaneously, forcing the airport to manage global traffic volumes on what is effectively a single active runway. In 2025, this facility facilitated 55.5 million passengers. On its busiest days, it processes over 1,000 aircraft movements in 24 hours. To achieve this, every integrated system, from ILS precision to wake separation, is pushed to its physical limit to land or launch a plane every 65 seconds. As physical space for new runways disappears, aviation infrastructure is moving into a digital era. This shift is led by the replacement of the iconic concrete air traffic control tower. Remote digital towers use slender masts topped with 4K cameras and infrared sensors to capture a 360-degree view of the airfield. Controllers manage the runway from facilities hundreds of miles away, using augmented reality overlays that track aircraft heat signatures even in low-light conditions. Inside the terminal, the physical boarding pass is being phased out through the OneID biometric system. Using cryptographic selective disclosure, a passenger's face becomes their digital wallet, allowing them to drop bags and clear immigration without showing a physical document. An airport is a mechanical organism that hides immense complexity beneath concrete and code. By coordinating millions of gallons of fuel, robotic logistics, and invisible radio frequencies, it makes the act of flying across the planet feel safely mundane.